Hi, this is a supplementary lecture to the Executive Black Belt course, or just really a general analytics discussion on a subject called transformations. Or another word for it is re-expression. Now, we're going to focus on a couple of things here. Sort of like, why would you want to do that? And then how, in a couple of different circumstances. Okay, so the two situations where we'll cover is in this is well. Let me just start by saying here's sort of the background of this, and that is that a transformation or a re-expression, a lot of people get kind of nervous about it, or they think it's fishy, or they think that there's something going wrong. But we're already actually used to transformations in everyday life. Let me just give you a very simple example. This is about as simple as it comes. I can express something, I can measure something, and I can say that it's an inch long. And if somebody comes to me and says, no, it's 2.54 centimeters long, we already know that that person or we have done some re-expression, and we're both right. Or we could both be wrong, I suppose, but we're both giving the same answer. 1 inch is actually equal to 2.54 centimeters. We convert between these things fairly naturally, and it's easy for us to do it. Same as converting from currency like dollars to pounds. That's a very simple transformation. Okay, so that's just the sort of the tip of the iceberg of transformations. There are other transformations that we don't even know about, like, for example, in acoustics, or the study of acoustics, or the reporting of how loud something is. The standard way of doing that is listing it as a ratio. So when we talk about a rock group like The Who, it used to be talked about how The Who is the loudest rock group. We look at that as a ratio of powers between what sort of sound waves hitting our ears, if we want to look at it scientifically. And we look at the ratio of the power that The Who was generating in terms of what was hitting our eardrums compared to, say, the sound of a normal conversation. So we would look at that ratio of powers, say power 1 to power 2, some reference, I'll call it power reference. But we look at it in decibels. It turns out that something like, instead of saying The Who is 100 million times louder than that normal conversation, we might say that The Who is, say, 100 decibels louder. So it makes this really large number more accessible to us. And so that's one of the reasons why we use it. Another place where we know about essentially a log transformation. A decibel is an example of a log transformation. Another place where we use sort of like a log transformation is in the Richter scale in earthquakes. It turns out that, for example, to go from a 5 to a 6 isn't an increase in intensity of simply a factor of 5 to 6. It's a factor of about 32, and that turns out to be an approximate logarithmic scale, or it is a certain type of logarithmic scale. In any case, we're used to these sorts of things. If you're in engineering, you're very used to this concept. The general concept of why you'd want to do a transformation is exactly the same as to an analyst, to a data analyst, as lots of other things are in everyday life to us. So if you're not a data analyst, think of it in terms of, maybe think of it in terms of the following. If you're a Six Sigma or Lean practitioner, one of the things that you know is by looking at the world through a process lens, you can often provide a different perspective to understand things, and understand things more deeply in some ways, or maybe just in a different way, so that you can communicate and make powerful changes. It's the same way with the transformation with data. you're transforming it into something that makes the data more transparent to you, or maybe easier to manipulate mathematically, or maybe easier to see things. Okay? So that's the way we want to do it. And we're all familiar with that. You know, you have a doctor look at a cut, and the doctor sees all sorts of things that you don't see, and that's the value of it. That's the same with this idea of transformation. It's a trick. It's a trick in your tool bag as an analyst. So let's kind of look at the two cases where, so that's the what, or that's the why, and I want to add in the how, not only how but also when. So when does your spider sense tingle? When does your analyst sense tingle? That says, you know, maybe I want to get a transformation. I'm going to give two cases and two examples. Okay. The first when is, number one, is when I have skewed data. I'll just say skewed data. It doesn't have to be skewed data, but it's very often. Skewed data is making it hard for me to see. See details. Let me give you an example. So suppose I had data that looked like this, and I don't know what these could come from. Maybe what I'm doing is I'm plotting the earnings of CEOs of businesses, and way over here are like the Forbes top 100, and over here are sort of individual business owners, the people who own the Chinese restaurant in your town, and the gas stations, and the mom and pop stores. You know, and they're not getting rich, but we've got some people over here. It's really hard to understand, say, details over here. I don't see a lot of details here, and it's especially hard to see details over here. It's hard for me to see. So a transformation is going to do something. It's going to kind of squash these guys together, and then kind of spread it out so that we can see some things. I think an example will help. So let's take a look at that. And again, I want to emphasize that today we are looking at primarily the log transformation. So I'm going to be looking at logs. Doesn't sound that exciting, looking at a log. Okay, let's look at it through an example. Okay, so in this particular example, what we are looking at is the following. We have a company that looks at that puts things through procurement, like many things do, to make you know, if you want to get something, like you want to get the office supplies, or you want to get a new monitor for your computer, or you want to order chairs for your working group, you send it through procurement and they get it. Or maybe if you want to hire a vendor, same sort of thing. So we're looking at the time for a number of different transactions, the time that it took. I'll call that the service time, or the procurement time. Procurement time that it takes. And if we just had data that looked like this, we might be interested in saying what's the shape of the data and all that. Well, let's just go ahead and take a look. In this case, we have a num, right? So we might do a one num analysis if we're using Excel stats. Let's take a look at that. Here's my Excel stats. Sorry, it took me a little bit longer than I wanted to there. And let's go to procurement, select it. Let's take a look at the one num. Sure enough, and I'm going to, again, give myself a little room on the bottom. And, I don't know, 10 classes, 16 classes. That looks pretty reasonable. Okay, so certainly, let's take a look at, let's make this a histogram. Take a look at that. And I think that pretty much everybody who's looking at this point is going to realize that, yes, this certainly looks like it's skewed data. And in fact, if I wanted to draw a curve, I might draw, I think maybe people wouldn't argue with this curve. There's probably lots of other curves I could draw too, right? So the problem is I don't have a lot of detail on this, on that tail, and maybe even more than that, I don't have a lot of detail on what's happening within the bulk of the data. So one way of doing that is to take a transformation to be able to see a little bit more clearly on those. And sometimes different patterns will come up. Sometimes different things that you didn't know were present come up. And let's just try it. Let's just take a transformation, and we'll find out in cases where you have skewed data, a log is perfectly good. So let's go ahead and take a log. I'll show you how to do that and what it all means also. Okay, so here we are back in our program here, or back in our data file, and we're going to take a log. But before we do, I just want to tell you what a log is. First of all, there's a couple of different logs. The two most popular are log base 10 and log base E. This is for people like me, mathematicians. We love log base E. I'm going to keep us in the realm of log base 10 because I think it's understandable and in some ways a lot better anyway. So let's go to it. So let me give you the backdrop. Suppose I wanted to I posed you the question. I said 1,000 is equal to 10 raised to what power? Well, you'd probably say, well, that's equal to 10 times 10 times 10, and so it's equal to 10 to the third power. And you'd be right. But what if we wanted to ask that in a general way? It turns out that the log is the answer to question mark. Okay? So the log of 1,000, it turns out, if we want to write this in another way, the log of 1,000 is equal to 3. It's equal to 10 to the third power. I'm sorry, it's equal to 10. It's the answer that says what is 10 raised? What do I need to raise 10 to get to be 1,000? That's the answer to that. Okay, let's just try a couple more. We erase that, and let's just try log of 10,000. You should recognize that's equal to 4, right? It's 10 to the 4th power. How about this is maybe a little bit different one. How about log of 1,000,000? Well, that's equal to 6. So now you see that what we're doing is we're squashing. There's one thing that we're doing is we're writing a big number very compactly, right? It takes a lot less energy and time to write 6 than it does to write 1,000, and it takes and it's a lot closer. So 3 is a lot closer to 6 than 1,000 is to 1,000,000, right? So we're kind of squishing that scale down. I'll do one more just so that you get this one too. The log of 0.001. What is that? Well, it turns out that that's minus 3, right? 10 to the minus 3 power is 1 over 1,000, and it works that way. Okay. We'll write one more, and this is just to give you some thinking on this. The log of, we can also do things like log of, what's the log of 3,000? Equals question mark. Well, I'm not too sure, but I can put some bounds on it. I know that the log of 1,000 is equal to 3, and the log of 10,000 is equal to 4. So I don't know exactly what it is, but I know it's between 3 and 4. Okay, I know it's between 3 and 4, so that tells me something. Now, there's lots more to logs than just doing transformations, but we're going to stop there. The idea isn't to teach you all about logs. The idea is to get you through with understanding basically what it is and being able to use it, okay, and reason with it a little bit. So a log can help you. It squishes in the numbers a little bit. And we're going to see this. Okay, so how do you do it in Excel? Well, it's pretty straightforward. I'll blow this up so that we can see it. I'll call this the log of PT. Okay, and it's simply equal to this. Equals log, not L-O-O-G, not log, it's the log. And by the way, it has a number and a base. If you wanted to add in the base, like if you wanted to do a base E, which is approximately 2.718, wish I could forget that and purge my memory, but that's okay. It's there forever. Or we could put in the log of base 10. The default is 10. So we'll do that. And then we'll check to see that we got it, right? Okay, so it says here that the log of 389 is basically about 2.6. So let's think about that. Well, we know that the log of 100 should be 2, and the log of 1,000 should be 3. So the log of 389 should be in between those two numbers, and it is. Your intuition might be telling you that it should be less than halfway, but your intuition would be wrong in this case because if you don't understand logs, if you do understand logs, you'll know that they're curved. Anyway, that's neither here nor there. Should be in between 2 and 3, and it is. So let's go ahead and copy that down all the way to the bottom. And the claim is that what I've done is I've taken something that's skewed and I've made it less skewed. Let's see if that's true. So if I do one num, I can replace that. Now, this is our original procurement. Let's take a look at the log of PT. And voila, look at that. Check it out. We did, in fact, make it so that it's all squished, right? And, in fact, we can see something that we couldn't see before. Isn't that cool? That's pretty cool. So if I were on a process improvement mission, I might want to say, aha, I don't have any other data, but I'm questioning maybe I've got data in a couple of groups. So I want to brainstorm why these data are grouping. You know, maybe this, remember, this is procurement. Maybe this is a type of procurement. Maybe this is all vendor, and this is all, materials. Or maybe this all requires a signature from compliance or from legal or from marketing or who knows what, right? Needs some signature, and this does not. Okay, so again, it's not going to tell you why there's two humps, but look at that. It gave you something, it gave you sort of supercharged your eyes so that you could see things a little bit better. To show you pictorially what's going on when you do a transformation, as we move from sort of, when you do a transformation, let me show you what that looks like. Here we have something where, in fact, I've got a normal probability plot there up there as well. I've set this up. This is a program called DataDesk where you can actually do transformation sort of live. I'm going to move this from 1 all the way to 0, and when we get to 0, that will be a log transformation. But you can see that these are intermediate transformations of different mathematical expressions. Oops, I didn't put on the automatic update. Let me turn on the auto update. There we go. I'll start from here. This is our original data of the procurement. And as I move toward the log transformation, you can see what's going on. I'm squishing in the right-hand side so that that long procurement time now is re-expressed as a number that's a little bit different. And my eyes are beginning to see better. Look at that. Now I've got those two vampire teeth kind of staring out at me. If I keep going, I can create a skewed distribution the other way. Not sure why I'd want to do that, but I could. There's my log, and I'm going to stick with it. Stop with the log. Now, there are some things that when you transform them, they actually become more symmetric or more normal. And a lot of people think that's maybe the main reason why you do a transformation. I'm going to show you one of those. and it can happen, but it's not the main reason. Again, I want to emphasize, you don't have to have normal data to do statistics. You don't have to. All right. Many things don't require that. But here's an example of data, and we're just going to do this 100% data desk. And this is from time to complete a medical service. There was an in-house, a county-wide health service, health system had a in-house health service that they could administer care in the home for non-threatening non-life-threatening medical conditions, some of them. And so in this, you would request for the service, and then they would show up within so many hours, and they were looking at, say, 24 hours thing. And in this case, if we did a histogram of that, it looked somewhat like this. And I could do a normal probability plot to show you the data are not normal at all. Where are you? There you are. Do my little Box-Cox transformation, which I'll do the log. And regression line, okay. You know, I turn on the automatic update. Turn on the automatic update. Good, good, good. And, oh, let's turn on the red. Not sure why I like the red, but there, I turned on the red. Oh, not sure why I can't do that. Okay. Just come back to here, and let's check out to see when we do that transformation. In this case, when we do a log, bam, the data turn out to be much more normal. There's my normal probability plot. Look at that, all along that line. Here's a histogram just kind of for general proof. Histograms are kind of crummy when you don't have a lot of data. Less than 50 data points is kind of rule of thumb. Yeah, we don't have anything that's even, you know, but it's certainly, there's no reason to reject normality here. When we look on here, yeah, the data look very reasonably normal. Normal is a pretty good model here. So that can happen, and we can do capability calculations if we wanted to in this re-expressed form. Okay, that's enough for that one. So there we go. If we ever wanted to get back to the original from the log, like if we did something to it, like we added 10 to it, or we fit it to some other thing, we fit it to a model, we got a number, we can transform back by simply taking 10 to this particular power. So if I take the number 10 and I raise it to the power there, you'll see I get the original number back. There it is right there. See that? If I take 10 to that, I can get the original number back. Okay, so that would be helpful if you like plugged into an equation that the result of which was the log of something, and you wanted to go back to the original units. Like suppose you were predicting something in dollars, and you wanted to get back to the original units. You could do that by taking 10 to the x power. We're going to actually do that in an example. So that's the first example, I think, and hopefully what you got out of that was that when you do the transformation, it can sometimes, you can start with something that you can't really see very well. I'm not sure why it moved on me there. Let me move it back. I probably touched it. This Excel is pretty touchy. Okay, I might start something where I can't really see over there, and when I take the log, I can start to see with clearer eyes that maybe it's a tool that it's like a microscope, or like Holmes's magnifying glass. Okay, so that's the first real reason. Now, I want to show you a different reason, but equally powerful, maybe even more powerful reason to keep it. So let's go back to our blackboard. Okay, so skewed data is making it hard to see the details. The second reason of when, and we're also doing the how at the same time, is specifically in linear regression, And I'll just say to to make regression more robust. Now we're also going to find, and this means when we look at the residuals specifically, when we look at the residuals, remember we look at the residuals to see if the assumptions of the regression model are met. When we look at the residuals, we'll eliminate patterns or eliminate patterns, or more importantly, eliminate the non-constant variance. Okay, so let's do an example of this. I think what you'll see will make sense. Remember, when we have the residuals, one of the patterns that we looked for was this non-constant variance. And this, you can think of this as follows. If this is my x and this is my residual versus predicted values, or residual versus the values I'm trying to predict, it turns out that, or this is my y predicted, that if I look at the residuals as my signal kind of goes up, my noise also goes up tremendously. You can think of it as, and I always think of these as alligator jaws. That's why I drew that in. But you can think of it as follows. Suppose you're listening to your stereo and you want to crank up the volume. That's like cranking up the number on your prediction, right? You're predicting larger and larger values, or you're using a larger and larger x to predict your y. That the error in your model keeps cranking up as you do that. Think of it as cranking up that stereo, and what happens is the more you crank up that stereo, you're cranking up the distortion in the voice as well. We don't want to do that. Good amplifiers and good stereos, you're able to crank up the volume without a lot of distortion, right? Really poor ones, like an old transistor radio from the 70s, when you cranked up that volume, that terrible distortion on what was going on. So we might want to apply a transformation to help us with that. Transformations can be very valuable in that. Let's take a look at that. And for this, we're going to look at some financial data from 1986. Now, that's a long time ago, and you might think things have changed, but you know, there's an expression. It's amazing how things change. When things change, how much they stay the same. We're going to look at an example from this. So in this case, we're looking at the Forbes data. Now, these come from Fortune 100 companies or Fortune 500 companies in 1985, actually, and they ran the gamut from technology companies to companies like GE, large manufacturing, to financial services, to totally service industry type things, airlines. So that's what we're looking at. And one of the things, suppose that you, now we're simplifying this to just have two variables, but in reality we'd have many variables. Suppose you were looking to predict assets given the sales data from a company. You know, what could you do this? Could you do this with a linear regression? Well, maybe. I know with you and I, we'd like to probably get more data, more variables, but let's just see if we can go ahead and do that by using that. So now we've got two nums, right? We've got a num and a num. So perfect case for a linear regression. Let's take a look at it. And oh my, here's our scatter plot. And remember, I might say that, yeah, I have a line. It kind of looks like a line there. Let me draw my guy here. It kind of looks like a line. But, boy, it sure looks like my prediction is not going to, I'm not going to be very comfortable with my predictions out here. And I do kind of see that fan shape. So when I do my regressions, I probably won't be able to, I won't be all that comfortable with the regressions out there. So let's go ahead and do it, though. Let's do the regression. So when I do it, yeah, I get that line that's fit. Okay, very cool. I should look at my R-squared. Turns out it's not very huge. There's my R-squared right there, 55%. But even if it were large, I'd still feel uncomfortable out there. Let me take my residuals. And yeah, there's that fan that I was seeing. I am really uncomfortable, especially with making predictions out there. If I were going to use this model, I'd like to be more comfortable. So sometimes when you have data like this, transforming the data can make it more comfortable. And I want to demonstrate that by using that other tool that we had before. So what I've got here is I've got, there's my, let me add my regression line. Or there's my, let's just use this scatter plot. There's my scatter plot of sales versus assets. And I've got my own transformation thingy going on here. And you'll see I've also got the histograms right here at the near the bottom of the page. And now here's my regression. You'll recognize this as being the same. And if I take a look at the residuals, they're gonna be just as bad as before. So one of the things I might do to make it more robust, as I said, to make it more resistant to the assumptions, is to transform. So I'm going to start by transforming. I'll transform my x variable to see if that helps. Here's my log. That's a square root. Let me go all the way to log. And there's my transformation of looking at the sales. Let's see what's going on. Oh, got some fixed scale problem going on here. Let me just go ahead and make the scatter plot directly. There we go. Turn on the automatic. I didn't know why it wasn't updating the scale correctly. So let's go back to our original. There's our original. Okay, you'll recognize that. That looks all very similar. So I'm going to start out by transforming the sales. I'm going to take the log of sales. And there you go. And you can see what I've done is I've shrunk down what used to be a huge number, like in 40,000, 50,000, and I've shrunk it down to converting it to like a number of 11. And you can see it's equalized. It's helped me see a lot of the more of the detail here. Now I'm going to, and it's also made the data happy circumstance. It made the data normal. You don't have to have normal data for in the original variables for a regression, but we want the residuals to be normal. And it turns out that your bets are better if everything is normal. Again, it doesn't have to be. I want to be careful to emphasize that. Let's see now when we transform assets as well, and look at that. So now I'm much more comfortable recommending that we do a regression here as opposed to regression in the beginning. I'm much more comfortable with saying, yeah, I'm fine predicting things out there. I have data that's there. Now, isn't that interesting how that all happened? I want to show you one other happy circumstance. I mean, really happy circumstance. You can start to pattern to that you see before. And this is pretty interesting. I find it pretty interesting. I'm going to use my lasso to circle a few of these points. Some of you might think that you see a pattern right there, kind of a linear lineup of companies that are overvalued in terms of their assets by their sales. And in fact, let's color those red. I guess we have Christmas colors, but in any event, in fact, the kicker, and the reason why I didn't tell you before, and why it all goes around, is it turns out that each and every one of these companies that's overvalued was a financial service company or a bank. And we all know about the great savings and loan scandal in 1986. A lot of these companies were heavily invested in junk bonds. And here's one place where you could actually tell where they really kind of stuck out like a sore thumb. But you wouldn't be able to see that without taking that log transformation. Okay, so hopefully that helps give you a good idea for why you might want to do that. And one last thing, let's take a look at the residuals just to make sure that the residual versus predicted did get better. And there we have it. There's our, whoops, I shouldn't have left in the, let me just take out those. The patterns are still there. And by the way, if you wanted to improve your regression, you might want to take into account whether making what's called an indicator variable of whether or not the company was a financial service company, and that might also help you make a better prediction for what their assets should be, and that would take out some of that in the residuals as well. But certainly this residual passes the sniff test of is this a reasonably robust model to use. It may not be a very good model. In fact, when we look at it, there's our R squared, 33%. We would certainly want to add more variables into this to make better predictions. So it's not a very good model, but I'm not afraid to use it. I'm not afraid to break it in the way that I was before. Okay, so so that's it. Now I just want to do one more, make one more comment. So to do that, I'm going to have to actually note what my coefficients were and what my constants were. So here I have log assets equals 3.5 plus 0.587 times sales, right? Times log sales. I want to make clear of this, right? Okay, so let's go back to our original data here, and what we did, and I want to make sure that you get this, is that we now have a model, but it's a little bit, and this is kind of annoying. I think you're going to get a little bit upset at me maybe. We have a model not for assets, but for log of assets based on log of sales. Yeah. So instead of our original thing, we have log of assets. I'll just call it L assets. LAS is equal to 3.5. This was the model that we just fit, plus 0.586. I'm sorry, 87. I'll just call it 0.59 times the log of sales. So this is the downside or the dark side of all this. You might ask the question, well, what if a company had 10,000? I think that the numbers were originally in millions. But what if a company had 10,000 in sales? What would be the assets that they would produce? We have to take that sales to log sales, plug it in, and then we get log assets, and we convert that to assets. Ugh. So how do we do that? Well, first, let me just do that, and I'll plug into the equation. Okay, let's just do it all in Excel. And first of all, I'll put in our handy dandy model. So our constant was 3.5, and our coefficient was 0.59, and then so I'll say here's the log of assets produced by the model, and then here's what assets predicted. Okay, so let's start out by plugging in, if we have sales, and I said it was 10,000, whoops, 10,000, right? Here I plug in equals the log of 10,000. So the log of 10,000 is 4. That makes sense, right? This just remains the constant. So my log of assets is equal to simply this, which is 3.5, plus 0.59 times my log of sales. Great. So it predicts the log of the assets would be this, and so what does that mean in terms of the assets? Well, that's equal to 10. That's equal to 10 raised to this power. I'm just going to reverse that out. 724,000, and that would be our prediction. Okay, in the original units. And again, we could now change these to, again, let's put in 1870, and we'll see that our prediction is probably going to be pretty close to that. Not exactly, right? We don't predict it exactly all the points on the line, but let's see how close we got. 1870. There we go. 269,000. The ones that are bigger are going to be pulled more. 90, 84, There we go. So again, that's going to be the prediction that we have coming in there. It's possible that I made a little mistake here, but I don't think I did. In any event, that's how you back it out. So again, certainly, I would hope that you do feel more comfortable, say, using this and feel that this meets the assumptions, and that, maybe more importantly, that you can really see this stuff, right? You can really see things that you couldn't see without taking that log, that you should feel more comfortable with that than you did with the original right here. Okay? All right. So, just as a quick recap, transformations. Okay? It's an analyst trick. It's not really it's not a trick to fool, and it helps us see better. For that, you should remember the procurement example and also the regression example where we found those financial services companies. And also, it helps a little bit with the assumptions. Helps with making robust models. And that's specifically in regression. We looked at that. All right, so I hope that you found this helpful and illuminating. Transformations, not all that complicated when it comes down to it. Try the log, okay? Try and get used to doing the log transformation. I think you'll find that in many cases where you have skewed data, it'll really help you understand and see your data a lot better than you have in the past. All right, take care, and hope you enjoyed the lecture.